Hello everyone, my name is George Dai and I am a junior at Texas A&M University. I will be presenting on the timeline and systematic implementation of Bitcoin's post-quantum security, which is the project that I did for the REU program at UT Dallas. So let's move on to the introduction. In this project, we will have four main parts, the first of which is quantum computing, which will decrypt the ECDLP, or elliptic curve discrete logarithm problem, which is problematic because the ECDLP is used to encrypt Bitcoin, and quantum computing can decrypt the ECDLP, which encrypts Bitcoin. So Bitcoin would need to use crystals dilithium, which is an encryption method that resists quantum computing. Now let's explain each of these parts more in detail. So quantum computing is basically just similar to normal computing, where the computers are made of qubits, of bits and quantum and logic gates. Quantum computers are made of qubits and quantum logic gates. Qubits have a little bit of a difference with normal bits because they can represent both a 0 and a 1 simultaneously, and quantum logic gates will take that into account when working on the qubits. So the logic gates and the bits will operate rather differently from normal computers. But because of this, there is a Shor's algorithm, which was created for quantum computing, and that could theoretically solve the ECDLP. However, Shor's algorithm has not been able to be massively run on quantum computers as of now, though research is being done to physically operate Shor's algorithm on a large scale. Now we move on to the ECDLP, which is the elliptic curve discrete logarithm problem, as explained earlier. The ECDLP is used both in ECDSA and Schnorr encryption, Schnorr encryption being the encryption that Bitcoin uses, and it is provably quantum vulnerable, as we see with Shor's algorithm. Mostly, the ECDLP could be solved by quantum computing in O log n to the power of 2 time, or logarithmic polynomial time, instead of classical computing solving it in square root of n time, where n is some very, very large power of 2. Now we move on to explain what Bitcoin is. Bitcoin is essentially a public ledger of blocks, and each block has a header and a list of transactions. Blocks have like an average size of 1.7 megabytes, and they also take an average of 10 minutes to mine, and then all those blocks would be connected in a chain, otherwise known as a blockchain. These transactions in the blocks are signed and spent with a public key and a signature. And currently, we are using Schnorr public keys and Schnorr signatures, which are quantum vulnerable. As in, a quantum computer can take your Schnorr key, Schnorr public key, Schnorr signature, and derive the Schnorr private key from it. Therefore, they could falsify their own signatures, rendering and spend your Bitcoin basically, without you ever knowing it. And then finally, that's why Bitcoin would have to use crystal dilithium, which is NIST, or the National Institute of Standards and Technology, their primary post-quantum signature scheme. This crystal dilithium is provably classically and quantum secure, and the only downside to using this signature scheme is that it has much larger keys than the ECDLP based encryption, being 1,312 bytes versus 32 bytes. This does pose a slight issue because, as we mentioned, blocks do have an average size of 1.7 megabytes and they cannot go above a certain size. So larger keys and larger signatures directly correlates to less transactions, which is a bit of a problem. However, we will address that problem inside of our roadmap, which comes a little later. Let's move on to our research questions. First research question is, how long until quantum computers could solve the ECDLP? I mentioned earlier that quantum computers can only do it in theory, but right now we are looking for an estimation of how long we have until quantum computers can do it in practice as well. And the research question 2 is how to implement Bitcoin's quantum safety, which we will answer in our overview as well. So now moving on to our overview for estimating quantum computers, how long they would take to solve the ECDLP, we will use both a practical estimate with existing Toffoli gates and logical qubits that have been created, and then we will use also a theoretical estimate, which is we will use the components that can be made into these Toffoli gates. Toffoli gates are a special type of quantum gate, which basically, if both inputs are 1, it will flip, if both bit inputs are 1, it will flip a third bit either from a 0 to a 1 or a 1 to a 0. And with these Toffoli gates, quantum computers can basically do anything classical computers can. So that's why we care about counting how many Toffoli gates that currently can be created, and also how many Toffoli gates that theoretically could be created if we were to use its components parts instead of to estimate instead of the amount that we currently can create. And next, we will have the estimated time horizon from our first step, and then we will create a two-phase roadmap for converting Bitcoin from the quantum unsafe Schnorr signatures to the quantum safe crystal dilithium. In this roadmap, we will use the philosophy of minimum viable change, which is just implementing the simplest change necessary. And we will also provide example code illustrating our changes that we suggest. In phase 1 of this roadmap, we focus on backwards compatibility with the current Bitcoin system while allowing users to access these post-quantum security measures. So old nodes won't actually have to update to still be part of the system, while the newer nodes can take advantage of what we add. And in phase 2, we will stabilize on a system that is similar to how Bitcoin currently works, with the exception that all Schnorr encryption is replaced with crystal dilithium. Moving on to how we conducted our estimation. Bitcoin uses a 256-bit ECDLP, and a paper published by the IACR gives this formula down here to find the required amounts of Toffoli gates to allow a quantum computer to solve a 256-bit ECDLP with n equals 256. This comes out to about 179 million Toffoli gates with a Toffoli depth of 3.5 million and a logical qubit count of 3,600 logical qubits. We will explain why the logical qubits aren't the limiting factor in our practical estimation, which we sourced from the Harvard researchers, their work in 2024, where they created 48 Toffoli gates and 48 logical qubits in the same experiment. And seeing as we only need 3,000 logical qubits but 179 million Toffoli gates, we could see that the logical qubits aren't really the limiting factor here. As aforementioned, the Harvard researchers were able to create 48 Toffoli gates, and they had a 450 nanosecond runtime per gate. This comes out to a total runtime if you ran all of these Toffoli gate and Toffoli depth, Toffoli gate times Toffoli depth, if you ran all those operations, it will come out to 59 million seconds about. We want to push this 59 million seconds to under 10 minutes because, as aforementioned, a block is mined every 10 minutes. Before a block is mined, the attacker could try to decrypt your private key from your public key and signature and basically forge their own transaction to their own bank account or their own Bitcoin account and whatever. If they are able to do it in under 10 minutes, and if they broadcast that transaction, then you would be losing your Bitcoin pretty much. So the time it will take we estimate the time it will take for us to create a machine that could solve this 256 ECDLP in under 10 minutes. We estimate that to be 13.26 years in the future in our practical estimate. So basically, we don't need to worry about this for 13.26 years if we use this estimate. Now, for the theoretical estimate, we use Google's quantum supremacy experiment done in 2019. In this Google quantum supremacy experiment, they created 36 Toffoli gates, or they created the component parts enough to create 36 Toffoli gates. They didn't actually create these gates, but they mentioned how many component parts they did. And using a conversion rate of 1 Toffoli gate from 6 C0 gates and 11 single qubit gates, we were able to come at the estimation that they created 36 Toffoli gates with a 569 nanosecond runtime per gate. This comes out to a total runtime of 9.9 million seconds. And since this experiment was done in 2019, we estimate that 8 years from now, from 2025, the quantum computers will be strong enough to solve the ECDLP 256-bit ECDLP in under 10 minutes. So we arrive at a timeline for our roadmap phase 1 of from now until the ECDLP is easily solved, which we predict to be 8 to 13 years. And the goal for this roadmap phase 1 in this timeline is to maintain backwards compatibility with current Bitcoin systems while allowing users to access post-quantum security measures. And this implementation is a soft fork because of backwards compatibility. As aforementioned, old nodes do not have to update to stay within the system. And so this soft fork is very optimal because we are able to keep the majority, we're able to integrate this into Bitcoin without requiring any changes, really. What we are implementing is a new Bitcoin opcode to verify dilithium signatures called opcheck dilithium sig, similar to the one that they use to check Schnorr signatures they use right now, and a new hybrid wallet, which could use Taproot script to allow for either Schnorr or dilithium spending, depending on Schnorr or dilithium signatures when you sign transactions. And the main drawback of this roadmap phase 1 is that users are initially disincentivized from using dilithium signatures because the larger size of the signatures directly correspond to higher cost, and not many people would be updating their nodes to check for to allow dilithium verification, which means that there's lower support. However, as time goes on and as the quantum threat grows more evident, more nodes would be supporting dilithium signatures and more people would use our roadmap phase 1 as well. So next we will move on to explaining exactly how these two changes are implemented. First, let's define the script path. We mentioned that our hybrid wallet has two script paths, one for Schnorr spending and one for dilithium spending. Our Schnorr script path is up here. Note that it is just the Schnorr public key and then you do an opcheck sig. Remember this opcode. And the dilithium spending path is it pushes the data of the dilithium public key onto the stack and then it performs opcheck dilithium sig. Note that opcheck dilithium sig is the opcode that we propose to add. Now with these two script paths, we insert it into the hybrid wallet verification pseudocode. As you can see, we will insert both script paths and, we will insert both scripts. And if the script is Schnorr, we use the Schnorr script. If the script is dilithium, we use the dilithium script. So as you can see, if it's Schnorr, you use this one. If it's dilithium, you use this one. And now we will just push a few things onto the witness stack. If it's a Schnorr, if the script path is Schnorr, it will have a witness stack that looks like this with a Schnorr script, Schnorr signature, Schnorr public key, and control block. And if it is dilithium, it will look something like this with the dilithium signature, dilithium pub key, and control block. Control block is simply simply a mechanism to verify that the user does know both script paths without revealing this the hidden script path that you didn't use. Now we have this witness stack. We will insert that witness stack into the process stack and script functionality. Basically, we check which script we're using, and then if there is an opcode in the script that is opcheck sig, we perform this opcheck sig function, and if it's opcheck dilithium sig, we perform opcheck dilithium sig function. And we look over here, we see that opcheck sig pops the signature and the public key off the stack and then verifies that the signature matches the public key. Similarly, opcheck dilithium sig pops the signature and public key off the stack and checks if uses the dilithium verification to see if it checks out. And then we will, at the end, we will pop the control block and then check if, verify that we do in fact know both scripts. So the spending is not falsified, so to speak. And mostly just note the similarity between Object-SIG and Object-to-Lithium-SIG. We did mention earlier that Object-to-Lithium-SIG would be based off of Object-SIG, and as you can see, this is the case. And with that, we have implemented our 2 changes that we suggest in the roadmap phase 1, mainly Object-to-Lithium-SIG opcode and also a hybrid wallet functionality. Now we move on to roadmap phase 2, which has a timeline of after the ECDLP is solved by quantum computers. And our goal here is to move away from the Schnorr signatures to the quantum safe crystals to lithium, but keep everything else the same. So every Bitcoin system that doesn't need to change wouldn't change, but we will change everything that is needed to support a new crystals to lithium signature scheme. This implementation is a hard fork because we are completely overhauling the entire signature scheme, and we will basically be deprecating the Schnorr signature scheme permanently. So first of all, as we mentioned, we will retire or burn all Bitcoins and wallets with exposed Schnorr public keys simply by denying any transaction if the Schnorr key has already been revealed. This is to prevent people from lessen the incentive of people trying to decrypt Schnorr signatures, basically. And then we will also use a commit delay reveal protocol, which we will implement later, which you will see the code implementation later. We'll use that for unrevealed Schnorr wallets, which is we use the op-return opcode so users can predetermine a quantum safe wallet as the destination of a Schnorr key transaction. Even if the Schnorr key is unsafe, they will be able to complete this transaction safely without people stealing from their Schnorr wallet, basically. Finally, we will define a new address type P2DIL for dilithium only transactions and deprecate all other address types aside from P2TR, which is used to support our hybrid wallet. And we will update all participating nodes to adopt this dilithium verification, and we will change the maximum block size to 17.7 times the original block size to account for the increase in transaction size of dilithium transactions compared to Schnorr transactions. So for our phase 2 implementation, let's first look at our commit delay reveal protocol. In our op-return commit script, we will hash together a Schnorr public key as your sender's Schnorr key, which is unsafe normally, as well as a hash of the dilithium public key or the safe public key of the receiver that they wish to send to. And then we will commit it and put it into a dictionary. And in that dictionary, we would also record the block height that this commit script was written in. After enough blocks are mined, the commit would basically be confirmed, and then the user could send the transaction. So let's look at what happens if a user does send a Schnorr transaction after they have already made a commit. The process would actually be very much similar, as in the witness verification and the process script function that we showed earlier. They would stay exactly the same, but we would only need to update Object-SIG so that it no longer takes in Schnorr signatures, as those are no longer safe, but it will just take in the hash of a receiver's public key. And we see that we see a hash of the receiver's public key, and then we could recreate the hash that we made earlier. Specifically, we could recreate this hash right here. And then after we recreate the hash, we could see if the public key has been revealed. If it has not, we could check if the hash has been committed. And if it has been committed, we could see that if it's confirmed by having enough blocks mined after it. And if all of those come through, then we will return true and verify this transaction. Otherwise, we will return false and not verify the transaction. Finally, continuing on with the implementation, implementing the 17.7 times block size increase is very simple. We simply just go to Bitcoin Core's consensus.header file and change this variable from 4 million to 70.8 million. And then to implement the P2DIL address type, we just combine pay to taproot and pay to witness public key hash protocols, basically using pay to taproots or just taproot's transaction formatting with a few minor adjustments. Simply going to change the input witness field to dilithium instead of Schnorr signature and dilithium public key instead of Schnorr public key. And we'll change the output field from a Schnorr public key to a double hash dilithium public key. Basically, the sender, the sender Schnorr and Schnorr signature, Schnorr public key are changed to dilithium, and the receiver's Schnorr public key is changed to dilithium. And then we will similarly use a Bech32M encoding with version 2 instead of Taproot's version 1 to encode this double hash dilithium public key into the address. And if you need a full Python code implementation, you could go to this GitHub repository where everything is stored and labeled. In conclusion, we have successfully predicted that quantum computing can solve the ECDLP in 8 to 13 years, which means that Bitcoin would be unsafe in 8 to 13, or Bitcoin encryption, Schnorr encryption would be unsafe in 8 to 13 years. And we have created a two-phase roadmap for Bitcoin's transition from the quantum unsafe Schnorr keys to the quantum safe crystal dilithium keys. Future work can center around how some layer 2 systems would interact with the new crystal dilithium keys that we wish to implement, as currently layer 2 systems are all based on Schnorr keys. And future work could also look at how to fully implement code in Bitcoin C++ source code, as the code that we have here is in Python and is not fully integrated into Bitcoin source code. And finally, here are all of the works cited used for this presentation. Thank you so much.